Everyone, good afternoon. My research topic is wireless underground sensor network using acoustics for agricultural purpose. So globally, farmers have range of sensors, but still they are reluctant to use those. Why? Because existing wireless underground sensor networks has above ground telemetry nodes, solar panels, and other devices that creates a navigation hazard and are prone to get disconnected. So the only solution is to put all the devices underground, and create a below ground to below ground communication system. However, the most current result from RF communication tells us that the maximum range can be achieved is 20 meters, which is not enough. So we need to investigate other alternatives to make it viable. And before going to the next technology, we need to know what are the requirements for wireless underground sensor communication. It needs to have a greater communication range, preferably more than 50 meters, and it has to be small enough to put in a borehole, and it should be operable under varied soil condition and moisture condition. So keeping those things into our mind, we have investigated that and found that acoustic technology has the potential to overcome the challenges that we talked about. It can communicate more than 50 meters of range and does not require any antenna. And the devices are small enough to put in small borehole. But still, this technology has not been investigated for agricultural purpose. That's where my project actually comes in, and where I will be investigating the whole thing in 3 steps. In the first step, I will be investigating a theoretical model or mathematical model to estimate the acoustic signal attenuation and also explore the characteristics of acoustic signal propagation. In the next step, I will be, I have done the testing of all the devices in a smaller lab environment, control environment. And last but not least, I will do the field test where I'll be taking the whole technology into the agricultural field. So far what I have achieved is I have done the first phase, and I have found that if the frequency of the acoustic signal increases, the signal will degrade faster, which means the transmission range will reduce, and there is an impact of soil texture. If the clay content increases, the signal will degrade quicker. So from these 2 graphs, we can clearly see that in the clay type of soil, 40 Hz signal can be transmitted up to 55 meter, whereas in the sandy loam soil, that can be transmitted up to 90 meter. And in the lab environment, I have tested my transmitter and receiver, and we have found the similar characteristics that if the frequency increases, the signal will attenuate faster. And the most interesting thing here was this laboratory test also supports the hypothesis that acoustic communication has the potential to achieve the range that we require. And this is another test that I have done to find out if any encoding system can improve the transmission range. And I have found that instead of using 1 thrust for 1 bit of data, if I can do 4 thrust for 1 bit, that will be detectable for longer range. And my future work involves taking the whole technology to the agricultural field to see the impact of moisture and compaction, and that will help us to design a topology to see if we can reduce the number of sensors. And last but not least, I will investigate the power efficiency of the whole system. Thank you so much, and I would like to thank Soil CRC and Richard for helping me. Thank you.